Alright, hello everyone. This is the, I believe, 2022 fall final exam, and let's just get straight into it. Number one, find an equation of the tangent planes of the paraboloid z equals 1 minus 1 over 10 x squared plus 4y squared. Okay, so we can rewrite this in a pretty easy format where we get 0 equals 1 minus 1 over 10, 1 over 10 x squared plus 4y squared, not a vector, minus z, and that we can just call it f of x, y, z. That just makes things much easier, and we can find the gradient t f of x, y, z, and that is just given by negative 1 over 5, negative 8 over 10, so that's just 4 over 5. I can rewrite that, negative 4 over 5, and of course negative 1. So we know that the plane equation is negative 1 over 5 times x minus 1 minus 4 over 5 y minus 1 minus z minus 1 over 2 equals 0. And of course, I think what they did in the solutions is they multiplied the whole thing by negative 1, or they just added everything to one side. So we know that our I guess the direction for the x should be 1/5, or at least some of it. The magnitude should be at least 1/5, and for y it should be 4/5. So C is wrong, A is wrong, and D is wrong, and that just leaves us with, and actually E is wrong as well. So there's only one answer that has the correct, and that is B here. So B should be our answer. Number two, find the points where f has a local extremum for f given by fxy equals negative x cubed plus 4xy minus 2y squared plus 1. So again, we need to take the gradient of f to find the critical points, and let's just do that. So we get grad f x y equals negative, or if I would write out the angle, okay, 3x squared plus 4y, 4x minus 4y. Okay, very nice. And now we need to set each of the components equal to 0 so that we have, 0 equals negative 3. What is happening here? Okay, negative 3 x squared plus 4y, and of course 0 equals 4x minus 4y. So if we, I guess, focus on this equation, we're just going to get 4y equals 4x, and therefore x equals y. That makes things much easier. We can plug in x equals y to this equation right here, and that'll capture all our solutions here, and that is, of course, very nice. So I'm just going to plug in x over here for y. So we're going to get 0 equals negative 3x squared plus 4x, and we can pretty easily factor out a negative 3x, so we're going to get 0 equals negative 3, negative 3x, I even said it, I just didn't do it. So x minus 4 over 3, and we solve, we're going to get x equals 0, x equals 4/3, and I'm just looking at the answers. That looks like we're doing something right because we have 4/3 here and 0 here. So looks good, but now we need to find fxx and fyy so we can compute the determinant, or the kind of the curvature, how the graph looks at these points. So fxx is just going to be negative 6x, and luckily it's pretty easy. Fyy equals negative 4, and we also want fxy, and it's also worth noting that just equals fyx, and that will just be given by 4. Very nice. And if you remember, d, or whatever we're going to call it, is just going to be fxx fyy minus fxy squared. So if we plug in our values, we're just going to get 24x minus 16. Very nice. Okay. And if we plug in our points here, of course, we can just transform these into actual points, but we don't even need to because there's no y in this right here. So we're going to get, for x equals 0, we're going to get a negative value. So that means that's a saddle point. So we don't really need to consider that. It's neither a local minimum nor a local maximum. So that is pretty simple here. And if we plug in 4 over 3, we're going to get a positive value for d, which means that it's it could be a local minimum or maximum. And I mean, that's pretty obvious because if you plug in a value greater than 1 here and subtract 16, it's going to be greater than 0, and that's what we're looking for. Now we need to just look at fxx or fyy just to see if it's a minimum or maximum. So if you think about it in 1D, if you just draw something like this, if it's, say, if x, or if you have just y equals x squared, and then you have something like this, obviously, I shifted it a little bit down, but on this graph, y double primer, I guess you could do like d squared y dx squared is going to be greater than 0 because the slope is getting greater and greater, and it's pretty analogous to partial derivatives and we're in the third dimension. So as we can see, it's going to be negative here, and negative is just the opposite of what I drew here. So that means we're going to have kind of something like this. So it's going to be a local maximum at x equals 4/3. So it'll just be 4 over 3, 4 over 3. And I said maximum, so it looks like it's E here. Number 3, find the work done by the force F equals -1/2 x, -1/2 y, 1/4 on a particle as it moves along the helix. R of t equals cos t sine t. Okay. I think it's always good to check if the work or the force field is conservative. Just makes things so much easier. And if we write out our force in angle notation, how I like it, we're gonna have 1/2 x, -1/2 y, and 1/4. And as we remember, we could compute the curl, or also there's a shortcut. If we just take two components, say the x and y component, say we call this f, say we call this g, and g is obviously the y component of f. We need to have kind of like the opposite components and of the opposite partial derivatives equaling each other. So I guess if I give an example, it might make it a little bit easier to understand. So in this case, we need to have f of y equals g of x. And in this case, f of y is 0 and g of x is 0. So that checks out. What we're doing here is just actually like doing what you would do if you computed the curl. So that's worth noting, but this is just a quick shortcut. And if you call this, say, the last component h, another example would be f of z equals h of x. So we're really just taking this component and looking at the opposite one, which is z component, and doing that partial derivative. So in this case, f of z is 0, f of h of x is 0, so that checks out. And if you do that for all those, they should all check out. So that just indicates that this is a curl-free vector field. Also, I mean, if you graphed it out, it's just like it's not really going to be curl-free, just because our vector field is really, in essence, the shape is just -x, -y, and that doesn't really have any curl. That really just has. So if you're over here, it's really going to be something like this. It's going to be all going to the center, or maybe not. I'm wrong, but if you had a curl, it would be something like where it would be like yx. That would create some sort of like circle vector field, and that's by definition what a curl is. So yeah, we can find the potential function where grad of the potential equals f, which is very nice. So we know that by this statement, potential sub x with respect to x is just going to be equal to 1/2 x, and that means we can integrate that with respect to x, which should just be -x²/4. And we can do the same thing for each other component. So phi, or potential with respect to y, is -1/2 y. That means the integral would just be -y²/4. And same thing for z. It's equal to 1/4. So the integral of that is just z/4. And what you have to do to find the actual potential function is just add together like all the unique terms. And since all these are unique, we really just add together all these terms. So we get x²/4 minus y²/4 plus z/4. And we just have to evaluate this from the point -1. This doesn't look too good. -1, 0, 3 pi to 1, 0, 0. And it shouldn't be too bad here. It looks like the y term is completely going to go away because the y is 0 on both bounds. And our x bound looks like top minus bottom. We're going to have negative 1/4 plus 3 pi over 4, and that is just all minus just minus 1/4, negative 1/4. And that means that it's just going to be equal to 3 pi because these just cancel. 3 pi over 4, and that looks like it is C. Number 4, let f be the conservative vector field given by fxy equals y cubed plus 1, 3x y squared plus 1. Consider a semicircular path C1 from 0, 0 to 2, 0. That is, C1 is given by r of t equals 1 minus cos t, sine t, 0 is less than or equal to t, is less than or equal to pi. Evaluate f dot dr. Okay. It's saying it's conservative, so we can pretty easily find the potential function, and potential is just going to be given by, or more correctly, it will be grad of potential equals the force field. And since we have our f, we know that our potential with respect to x is going to be equal, well, what is happening? Okay, it's going to be equal y cubed plus 1, and that means we can basically integrate this whole thing right here. And if we integrate it, we're going to get xy cubed plus x. And we can do the same thing for the y component. The potential, or phi with respect to y, is just going to be 3x y squared plus 1. So if we integrate that with respect to y this time, we're going to get xy cubed. It's not a good depiction. Okay, plus y. And to find the actual total potential, we just need to add together the unique terms. In this case, xy cubed is not unique, so we're just going to add it once. It's going to be xy cubed plus x plus y. And we need to evaluate that from 2, 0 to 0, 0. And it looks like the y in any case is going to drop out, so we can just scribble that out. It doesn't really matter. And it looks like this is just equal to 2 d here. Number 5, consider the circle C centered at 0 with radius 3. A particle travels once around C counterclockwise. It is subject to the force f of xy equals y cubed x cubed plus 3xy squared plus 1. Okay, is that the same as this? Oh, it is. Very similar. Okay. Use Green's theorem to find the work done by f. I was like graphing it, so if we graph it, it's just going to be some sort of circle like this. And good thing it's counterclockwise because Green's theorem says it should be counterclockwise. So we know what we're really looking for is, if we call like this component P and this component Q, we're looking for double integral. Let's call this the region D of del Q over del X minus del P over del Y. That dA, and del P over, or del Q del X should be pretty easy. It's just going to be 3y squared, and then minus del P dy. It is just, oh sorry, no, I didn't, I forgot, missed the x cubed term. It's going to be, I'll just write out the integral sign again, I guess. D, it's going to be 3x squared plus 3y squared, and then that is minus 3y squared. So these evidently drop, and we still are dA. So we're really just looking for integral of 3x squared dA, and I think it makes most sense to use polar coordinates. So in this case, we're going to use x equals r cos theta. Doesn't really matter. We could use r cos t, whatever. And plugging that in, we're going to get 3 integral. Of course, when you're getting 3x squared, so we're going to get r squared cos squared theta, r dr d theta. Don't forget that r here, just because of the transform. So r is going from 0 to 3 because it says radius 3. Theta is 0 to 2 pi. Pretty standard here. So we really have, if I just, I guess, make it a little bit more simplified here, we're really just integrating r cubed cos squared theta dr d theta. And a good identity, or I guess common integral to remember, is integral of cos squared theta from 0 to 2 pi. 2 pi, not pi. Okay. 2 pi d theta is just pi. And so what we can basically do here is we can really do 3 times integral 0 to 2 pi cos squared theta d theta times integral 0 to 3 of r cubed dr. And that's just because, I mean, if you do it out, you're going to get the same thing anyways. And that's just because, I guess, if the bounds depended on r or whatever, the variables, you couldn't do it. You'd have to do it in order. So if here, in case there was like a theta, you couldn't do it just because what you compute from this integral would, or I guess, feed into the next integral. So you couldn't do it. But in this case, we have constants. So if you have constants, you can pretty much always split it like that. And like I said, this, I guess this integral right here is just 2 pi. So that makes it pretty simple here. So we're going to get 3 times 2 pi times this integral right here, which should just be r fourth over 4 from 3 to 0. And that is 3 to the fourth is 81 over 4. So if we just make this, cancel this 2 and just make this a 2, it'll make it a little bit easier. So we're really just looking for, let me just make sure. Okay, I guess if we just get rid of this, and we have 6 pi times 81 over 4, or wait, 3 times 3, 9, okay, times 81 over 4. I guess we can simplify that to a 2, simplify this to a 3. We're going to get, okay, I think I messed something up here, but okay, just retrace. We have 3 times 2 pi, or no, sorry, okay, it was just 3 times pi because I forgot this integral was pi, not 2 pi, times r to the 4 over 4 from 3 to 0, and okay, now it's making sense. Now we're going to get 3 pi over 4 times 81, which is, should be 343 pi over 4, and okay, that looks like it's C. Okay, that's why I was a little confused. Number 6, find the arc length of the curve r of t equals 12 sine t, 5 sine t, 13 cos t from t equals 4, pi over 4 to t equals 5 pi over 4. Okay, so we know find arc length, it's just integral from some t. I'm just going to leave it empty for now. It's going to be r prime of t dt. And of course, you need to fill out the bounds, but we will, that just, I guess, 5 pi over 4 to 5 pi over 4. So finding r prime of t will be in our best interest first. That'll just be 12 cos t, 5 cos t, and okay, I'm going to fix that t here. It doesn't look like a t. Okay, 13 sine t. And then we can, of course, find the magnitude of that. So drawing a big, nice square root, we're going to get 140. Whoa, okay, we get 144 cos squared t plus 25 cos squared t plus 169 sine squared t. And if we use our identities, we're going to get 169 cos squared t plus 169 sine squared t, which we can just simplify to 13. It's very nice. So really just integrating pi over 4, 5 pi over 4 of 13 dt. And whenever we see something like this, there's no t inside of here, we can literally just do top minus bottom in our bounds. And that is just pi, so we get 13 times pi is our answer, and that is B here. Number 7, what value of c makes the function f of xy equals x squared minus y squared over x minus y if x is not equal to y, and cx equals if x equals y, continuous. So I think what we can do here is x squared minus y squared, we can rewrite that as x minus y x plus y over x minus y. Fix that here. And that just, if we cancel these, we're going to get x plus y. So really what we're looking for, like along the line, like x equals y, we kind of have like a discontinuity. So if we think about it, we're going around here, and then we're going here. But the problem is, if I draw the arrow here, I think it'll make more sense. The problem is that it's discontinuous here. So if x equals y, it's some constant times c here. And we want the limit as for this function, x squared minus y squared over x minus y, as we go from the line y equals x, we want it to be equal to this value right here, which is cx. So if we, I guess, do limit as along the line y equals x, so I don't know how I'm going to write that, but if we just do along y equals x, of course we're going x, or not really like that, but as x approaches y here, we want it to be x plus y. So that's our limit. We want that just to be equal to cx, or the actual value at that kind of point. And if we got this limit, we can just plug it in. We can either plug in, I guess we'll plug in x. Or I think actually what makes more sense is y goes to x. Same thing, but since this is x here, y goes to x makes more sense. So this limit's pretty simple to value. We can just plug it in. We can get 2x equals cx. And if we kind of inspect this, only c value that makes this true is c equals 2. And hopefully, yeah, c is our answer here. Well, c equals 2, okay. Number 8, choose a triple integral in spherical coordinates that represents the volume of the solid bounded by the cone. Z equals negative squared x squared plus y squared. And the sphere x squared plus y squared plus z squared equals 16. Okay. So I think it really helps to draw it out just to begin these. So if you have the cone like this, this should be straight down, but it's a little bit difficult to draw here. But okay, this is our cone here. And the sphere, this kind of, well, okay, maybe I should have, sphere should be like this. Okay, so the bounded, I guess if my drawing is not very good right now, but I think it will help if you draw kind of like a cross section. So let's consider this is the, let's say the YZ cross section. This is going to be our cone right here. And our sphere is going to be something like this. This is just the top half of the sphere, but we can complete it like this. That looks more like a ellipse, but it's all good here. Okay, and the area that we're looking for is the area bounded. So it's just this stuff right here. And okay, so since this is kind of like a normal cone where there's no like 3 times, or there's no like a times x squared plus y squared square root, it's just gonna create lines like y equals x. So these lines are y equals x and y equals negative x, and you can just get that by plugging in, like I found the cross section just by plugging in x equals 0. You can do the same thing and you'll get y equals plus or minus x. And in this case, of course, our rho value goes from 0 to 4 just because we're reaching the entirety of the sphere. So 0 to 4 is rho, and then phi should be, since like I said, it's going to be a normal. This angle should be from here. This is our phi value. This should be 3 pi over 4. And then, of course, it should go from 3 pi over 4 to the end, or the axis, and that is just pi. So our phi should be 3 pi over 4 less than or equal to phi is less than or equal to pi. And okay, that is phi, and then obviously 0 is less than or equal to rho, less than or equal to 4. So looking at our answers, B is not correct because we actually want it to be rho squared sine phi. and that's just the transform. C is wrong too for the same reason. It's not sine squared phi, and D is wrong because we're going from to 0 to pi over 4, which is wrong. So is E, so A must be our answer, and it looks like it is our answer. Number 9, integral 0 to 3, 0 to 9 minus x squared, square root 2x squared plus 2y squared, to square root 27 minus x squared minus y squared, xyz dz dy dx. When converted into cylindrical coordinates becomes what? And, okay, I think it always helps to draw out the dy dx portion, and we have something like this, but we're focused from x goes to 0 to 3, so we're really just focused on this. So our theta is going to go from 0 to here is pi over 2, so 0 is less than or equal to theta is less than or equal to pi over 2, and our r, of course, is going to be, it's 9 minus x squared, so 0 is less than or equal to r is less than or equal to 3. Just looking at, okay, E is wrong here, so is D, just because this is 0 to pi, and this is 0 to 9. And, okay, and now just looking at our z bounds, we know x squared plus y squared equals r squared, so we can plug in, of course, 27 minus r squared is our top bound. I guess if I can just write it like this, and then 2r squared is our bottom bound, or that just equal to r root 2. Make that a little bit better here. Okay, and now if we need to write these in terms of r and theta, we know x is going to be r cos theta and y sine theta. Multiply those together, we're going to get r squared sine theta cos theta. And in cylindrical coordinates, we just leave the z here, and we have r dz dr d theta. And don't forget that r, that's very important here. So we know an r times r squared should be r cubed. So we really should have r cubed sine theta cos theta dz, or times z dr d theta as our differential. And that means B is not correct here, and that leaves either C or A, and looks like C forgot the Z. So C is not our answer, A is our answer. Number 10, f equals negative y x z cubed, and S is part of the sphere. X squared plus y squared plus z squared equals 4 above z equals 1. With upward orientation, compute double integral of the surface S del cross f ds. Okay. This is quite the problem here, but I think we can simplify it. So if we intersect z equals 1 with x squared plus y squared plus z squared, we're going to get equals 4, so therefore x squared plus y squared, or not plus z squared, equals 3. And drawing it kind of in 3D, we're going to get some sort of sphere here, intersect it, so z equals 1. And that means if we kind of look it down from the z-axis, we're going to get some sort of just a circle with radius root 3. R equals root 3. And it's asking for del cross f ds. And by Stokes theorem, we know this. Make this a little bit better. It's just equal to the integral of the boundary curve, f dot dr here, and it's saying it's upward orientation, so that means we don't need to worry about the counterclockwise, because that means it is counterclockwise. So like this, and that means we can just evaluate the line integral around the circle here, x squared plus y squared equals 3. But then we know we can choose any surface that has that boundary curve and evaluate this integral right here. And excuse me again, I think surface that makes most sense to choose is literally just this kind of like, I don't know, this like disk or like circle solid thing in the xy plane that has equation x squared plus y squared equals 3 with r equals 3. That's because normal vector to that is just n hat equals 0, 0, 1. And that makes everything very easy because if we dot that with the curl, which we should probably compute now, we get del over del x, del over del y. Nope. We can, I guess, put negative y. And I guess I, j, k, matrix of that is going to be curl. And we, I guess, compute this. Partial root of z cubed with respect to y is 0, minus del z of x is 0. Partial root of z cubed with respect to x 0, minus partial root of negative y with respect to z is 0. Partial root of x with respect to x is 1, minus partial root of y with respect to y is negative 1, so we're going to get 2. And dotting these, we're going to get equals 2. So now as we chose the surface, oh, whoa, okay. We chose a surface, this kind of disk. We're really just looking for, I'm going to just write the s here, s of 2 ds. And integral, or I guess, since the integrand is constant, we can just pull that out. And we're just looking for ds of that surface, integral ds. And that's just the surface area, or the area of the circle. And since we know r equals root 3, and r equals root 3, and a equals pi r squared, we can just plug that in, and we're going to get the surface area, or the area of the disk, is 3 pi, and then we multiply that by 2, and we get 6 pi, so our answer is B here. Alright, number 11, find the area of the triangle that has vertices 1, 2, 1, 2, 3, 2, and 0, 2, 3. We know, just by definition, what is happening? Okay. The cross product is basically, if you have two vectors like this, cross product is, if you kind of like extend these, it's the area of the parallelogram kind of formed by these two vectors. So obviously this is parallel to this, like that. But if we divide this by 2, this is like the area of the triangle that's formed by these two vectors. So really what we can just do is, call this u, v. We can just do 1/2 times u cross v. And that should be area of the triangle. It's a little bit weird, but okay, it should work. So really just need to find that cross product. So if we consider this p, q, r, we can find pr and pr, or pq and pr. So pq is just 1, 1, 1, and pr -1, 0, 2, and we just need to cross these. So we get the determinant like I, j, k, 1, 1, 1, -1, 0, 2. Take that. We're gonna get I, so 2 minus 0 is 2. 2 minus -1 is 3, but don't forget the negative, so 3. And 0 minus -1 is 1. Okay, and now we need to get the magnitude of this, and that's just equal to 4 plus 9 plus 1, and that looks like that is root 14. And don't forget, we need to do 1/2, or half of 14, root 14. It's just, it should just be root 14 over 2. Hopefully that is an answer. Okay, D, yes. Our answer is D here. Number 12, find r of 1 if r double prime of t equals 12t squared and 1. And I'm just saying that in regular vector notation. And r of 0 equals j, and r prime of 0 equals negative k. Okay, I always like rewriting it in angle notation, so like that, and finally, okay, and looking for r of 1, so we're just going to integrate r double prime of t twice, which is kind of a pain, but we will do it. We have to. R should be, and remember we need to add our constant, so we want r prime of 0 to be equal to negative 1, and in this case, if we just close out the vector here, it's not going to be like that, so we really just need to add a negative 1 here, and in this case, if we plug in 0, we're just going to get negative 1. That's what we want. So that's looking good so far. Now we just need to integrate it again. We're going to get our, and in fact now we just want the middle term to be equal to 1, so I'm just going to keep that in mind. We're going to get 2t cubed t to the 4th plus 1. I'm just going to write that down right now because we know if 0 to the 4th is just 0, and we're going to get, okay, and just making sure if we plug in 0 to that, we're just going to get 0, 1, 0. Okay, that looks right. And then now we're just looking for r of 1, which is 2, 1, 2, and 2 squared 4 over 2. 2 minus 1 is just 1. Or no, sorry. We're looking for, no, okay. 1 squared over 2. Sorry, not 2 squared. So 1/2 minus 1 is just negative 1/2. And that looks like it is A here. Okay, 12 is A. 13, use the method of Lagrange multipliers to find the x components only of the points where the absolute maximum and absolute minimum occur for fxy equals x minus 2 squared plus y minus 4 squared on the curve x squared plus y squared equals 5. Okay, so we know if we just call g of xy equals x squared plus y squared, or minus 5, we're going to get, and we know the definition of Lagrange multipliers pretty much is just grad f xy equals lambda grad g xy. And that means we can just write two equations. 2 times x minus 2 equals 2 lambda x. That's just from these things right here. And 2 times y minus 4 equals 2 lambda y. Okay, it's nice. We can do some simplification here, cancel out the 2's here, makes things a little bit easier. And what I always like doing is just solving for x and y. It just makes everything so much easier. So if we have x minus 2 equals lambda x, we can do x minus lambda x equals 2, x times 1 minus lambda equals 2, and therefore x equals 2 over 1 minus lambda. And we can do the same thing for y. We're going to get y minus 4 equals 2, or no, we got rid of the 2. Lambda y minus lambda y equals 4. Therefore, y equals 4 over 1 minus lambda. Just is kind of the same pattern as the x's, just it's 4 instead of 2. Okay, now we can plug into here and solve for lambda. We're going to get 4 over 1 minus lambda squared, 16, equals 5. So we're going to get 20 over, and 4 equals, therefore plus or minus 2 equals 1 minus lambda. Set positive 2 equals lambda. We're going to get lambda equals negative 1, if I'm not mistaken. Yep, and if we set negative 2 equals to lambda, we are going to get 3 equals lambda, I believe. Yeah, lambda equals 3. Okay. And in fact, now we just need to plug in both values of lambda because it's asking for both values. Good thing we don't need to do any like checking. So this is our x value. We just need to plug in both values of lambda. Lambda equals negative, and we're going to get 2 over 1 minus negative 1. It's just 2 equals 1. And second lambda, we're going to get 2 over 1 minus 3 is 2 over negative 2 equals negative 1. Okay, so plus or minus 1 is our answer, and that looks like it is C. Number 14, reverse the order of integration and evaluate 0 to 1, x, cube root of x, to 1, 1 over 1 plus y to the 4th dy dx. Alright, so I was like drawing out the bounds. We're going y equals third root of x to y equals 1. Third root of x is something like this, and y equals 1 is also something like this. Make it a little more nice. Okay, and x 0 to 1, of course. Alright, so we're looking for something like this, but of course this integral is not the nicest to do. So we're going to go, like I said, we got x equals 1 here, so 0 to 1. Y is, okay. No, and now we're going, sorry. I think if we write it out a little bit nicer. Dx dy here. First, x is going 0 to, we have this. We can just cube both sides and get y cubed equals x. 0 to y cubed. And now y, as we established before, 0 to 1. So this is our new and actually possible integral. Makes it very nice. So we really just have integral evaluating the inner one. It's pretty easy because we just have no x's here, so we just do top minus bottom and multiply. So we're going to get y cubed over 1 plus y to the 4th dy, and to make this a little clearer, all right, we know that 1 over 1 plus x, integral of that is just ln absolute value x plus 1, and we can kind of apply that, as we can see, like clearly seeing some sort of chain rule going on here. But if we say we set integral, say we did ln of 1 plus y to the 4th, that would just be 4y third, or 1 plus y 4th. So we clearly need to just divide by a 4 here. Let me just move this up to make more space. Well, not that. Okay. So they're really just looking for ln of 1 plus y to the 4th. It should be over 4 from 1 to 0. And okay. Yep, that looks right. So we're going ln2 minus ln1, so that's just 0. Get that, and then over 4, of course. So our answer is A here. Nice. Number 15, evaluate the integrals 0 to root 2, negative 3 to 3, xy squared over 1 plus x squared dy dx. Okay, looks like we're going to be reversing the order of integration here, or are we? Let's just say no. We don't even need to do that. Okay. So we can really do something cool here. We can basically, this integral here, since none of the bounds include like x or y, we can just rewrite this as just write it like that. It just makes things a little bit easier, and that's just because, like I said, the bounds don't depend on any variables. So, like the previous integral doesn't feed into the next integral. Okay, so this integral right here is just going to be ln, so 1/2 ln of 1 plus x squared, and the 1/2 is just because chain rule, we get 2x over 1 plus x squared, so we just need to get rid of the 2 because we just have a 1x here. And we're evaluating this from root 2 to 0, and we need to multiply by y cubed over 3 from 3 to negative 3. I guess I can make this a little bit clearer here. Okay, this integral right here is, let's just try it, 1/2 times ln of 1 plus x squared, where x equals root 2, is ln 3. So ln 3 minus ln 0, so that's just 0, or ln 1, sorry, is just 0. So that, and then we need to just evaluate the other integral, which shouldn't be too bad, I think, hopefully. So it's 27 over 3, so it's 9 minus negative 27, so plus 9 over 3. So we have 18 over 3, or 18 over 2 times ln 3 is just 9 ln 3, or B here. Number 16, suppose that f of uv equals e to the v sine u, where u equals s minus t and v equals t squared. Find df dt when st equals 1, 1. Okay, you know this is going to be a chain rule type problem, so we know del f del t equals del f del u times del, or not del, times du dt plus del f del v times dv dt. And we know st equals 1, 1, so we can find u and t pretty easily just plugging it in. So we know u equals 0 because s minus t, 1 minus 1 is 0, and v equals t squared, so v equals 1. That's going to be helpful. Del f del t is del f del u, so we should find f of u, and that's going to just be e to the v cos u, and then also f of v here. F of v is just e to the v sine u. Doesn't really change. Okay. Now we need du dt, just negative 1, and dv dt is just 2t. Okay, and I guess evaluated at t equals 1 is just 2. I guess I can just write it like that. Okay. So now we're just looking for del f del t equals e to the v cos u times negative 1 plus e to the v sine u times 2. So we plug in 1 equals v, I guess, e times cos 0, so e cos 0 times negative plus e sine 0, which is just all 0, so this stuff all drops because sine 0 is just nice 0. So cos 0 is just 1, so this is just really negative e is our answer, so that is B. 17, let f of xy equals x squared times e to the x plus y. Find the unit vector in the direction of most rapid decrease for f when xy equals 1, 1. Okay, so really we're just looking for negative grad f xy over magnitude of f grad f xy. And that's just normalizing it. And the negative is because gradient points in rapid increase, but we're looking for decrease, so the opposite of that should just be decrease. So now we're just going to find grad f x y is going to be, we need to use the product rule here, so we're going to get 2x e to the x plus y plus x squared e to the x plus y, and for y, no product rule, e to the x plus y. Okay, now we're just going to plug in 1, 1 here. 1, 1 is just 2e squared plus e squared, comma, e squared. And that is just 3e squared, e squared. And like I said, we need to first normalize it, and then we can negate it. So the normal is going to be okay. We get 10e to the 4th root of that is just going to be e squared, but we need to keep the root 10. We can see that these actually drop. It's very nice. So we're going to get 3, 1 over root 10. And don't forget the negative signs finally. I just didn't include them until the end just to make it a little bit easier. So that should be our answer here. and it looks like A is our answer here. Number 18, find the centroid of the volume bounded by z equals 1 and z equals x squared plus y squared. Okay, this is going to be not too bad, but we should probably sketch it out. So x squared plus y squared is some paraboloid. You could use cross sections if you didn't know that. And I guess if we intersect that with z equals 1, we're going to get some sort of like kind of a bowl. So we're looking for the centroid. So first, what I like to do for these problems is, we know it's, if we draw like the xy cross section, we know parabola is going to be just circles, or this type of parabola at least. So just set z equals 0, and it's 0 equals, or sorry, just let z equal some constant. So it can be some constant equals x squared plus y squared. That just means we have circles. And that just kind of means that all like the, I guess, xy direction mass is going to cancel each other out. So our center of xy should just be 0, 0. So we know A and D immediately just cannot be wrong. And just looking at E, I don't think E is going to be the answer because we're ending at z equals 1, and it's very unlikely that there's going to be so much mass concentrated at equals 1. And in fact, the kind of mass density, it's constant. So E is literally impossible for the center of mass to be at z equals 1, because that's literally where we're ending our integration. And that's where the region ends. So that's going to be quite literally impossible. So now we should just integrate it. I have a hunch it's going to be C, just because it makes most sense that to 2/3, just looking at my drawing here. But let's do it out and confirm that or deny it. So we're going to be integrating. I think cylindrical coordinates makes most sense here. So if we just have z equals r squared 2, z equals 1 is our z bound. Theta, of course, is 0 to 2 pi. I'll just write that out right now. R is 0 to 1, I believe, because we're going, 0 to 1. And z, like I said, is r squared to 1. So we are integrating, or not z, we're integrating r dz dr d theta. And since nothing depends on theta anywhere, we can just take that out. So let me just make it a little bit more compact here. Let's put it like this. Okay, this too. Right. We're going to get 2 pi integral 0 to 1. Since nothing depends on z in here, we can just do top minus bottom. So r times 1 minus r squared dr, and that is equal to 2 pi. Oh, I'm messing up here. Okay. That is and 1/2 minus 1/4 is just 1/2, so the area is just pi. Or sorry, no, it's a pi. So 2/4 minus 1/4 is just pi over 4, so it should be pi over 2. Okay. No, pi over 4. Pi over 2, because 2 times pi over 4 is pi over 2. Okay. Now we need to find, I think it's the mass moment in the z direction, which will just be this integral, but instead of doing integrating rz, or, we're just going to integrate we're going to integrate r times z. And that's because we want to sum all the mass in the z direction, and then divide by the total mass to find the center of mass. So it's pretty analogous to the finding center of mass of x and y. So like x center of mass is like integral, I don't know what it is, but I'll just do it like this. X times like the density, which in this case is 1, dv over just dv. It's the same kind of concept here. So now we need to do the same integral, but z times that, which will make it a little bit more involved, but same, we can take out 2 pi. R same bounds, z is same bounds, but we just have rz dz dr. So this is just what I'm saying. It'll make it a little bit more involved because we have z now. We can't just do top minus bottom, but should be fine. we're just going to have z squared over 2, like this. So that would just make it, I guess the 2's just really cancel. So we're going to have, can't forget the z or the r here. Almost forget that. But we're going to have pi times integral 0 to 1 r times 1 minus r to the 4th dr. And that is just r minus r fifth dr. Same integral. I'm running out of space here, but let me just move it up a little. Okay. Okay, that's ample now. So we get r squared over 2 minus r to the 6 over 6. So 1/2 minus 1/6 is just 1/3, so we have pi over 3. And that is the like z center of mass, or the mass moment in the z direction, so pi over 3. And we're looking for, kind of analogous to this, we're looking for mass z over total mass. So mass z is pi over 3, and pi over 3 over pi over 2 is just 2/3. So our answer is C here. Number 19, let f equals ax cz minus ax cz plus by be a vector field where a, b, and c are all real numbers, or could be. Find conditions of a, b, and c so that f is not conservative, and such that curl f is parallel to k. Okay, so I think it's going to make sense if we compute the actual curl here. Excuse me. So we need to write our matrix out here, our supposed matrix. Del x, del y, and del z, ax cz minus ax cz plus by. So just the determinant of that. And okay, this should just be the vector b minus c del x of cz plus by is 0, del z of ax is 0, and finally negative a minus 0, so just negative a. And okay, so basically we want it to be parallel to k, but we still want a to have some value because it's saying parallel to k, and that means we need to have something like 0, 0, like c, I'm going to call it, some constant, be our vector, because that's the only way it's going to be parallel to k. If it's, say, 1, 0, c, it's going to be on some slight angle, and that's not what we want. So in this case, of course, a can't be equal to 0, because if a was 0, it wouldn't be parallel to k at all. So a can't be equal to 0. And then we also want b minus c to be equal to 0, therefore b has to be equal to c. That way, this ensures that it will be parallel. So we want this, and that looks like it is D here. Excuse me. Okay, number 20. Find the mass of the part of the plane z equals 8 minus 2x minus y that lines over the square 0 to 1, 0 to 1, where the density function is given by f of x, y, z equals 12 minus z. All right. Basically, what we're doing here is integrating the density function over the surface of the plane. So the surface is the plane. So really what we're doing here is just, if we call S the surface that is like encapsulated by the square. So like in this case, it'll be something like, just as a reference, let's just say the plane is something like, nope, not again. Okay, just say it's something like this. It's really just going to be, and this is the box. It's going to be like something like that on this plane surface. Okay, hopefully that kind of makes sense. Yeah. So, and we're going to call this surface S, and we're really looking for, we're just integrating, we're literally just doing this, 12 minus z ds. We're just integrating, we're integrating it over the surface, the density. So we're finding, I guess, the mass of that specific part of the plane. So to, I guess, convert ds into dA, we know in separate integrals, ds equals square root 1 plus zx squared plus zy squared. And that's pretty analogous to, if you think back to like arc length. Arc length is like 1 plus f prime of x. It's pretty analogous, but it's just in 3D. So I thought that was pretty cool when I first learned it. Yeah, so if we calculate zx in this case, which is going to be -2, zy is just -1. So we can do our ds pretty easily. 1 plus 2 squared, or -2 squared, is 5, plus 1 is going to be just root 6 here, so dA. So ds is root 6 dA. And now we really just need to, we have to plug in our z value here, just because we're going, if we write out the integral, we're going 0 to 1, x and y go from 0 to 1. We're going dA is just dA is equal to dx dy. So we can't have anything in z. So really we're going to have 12 minus z. So 12 minus 8 minus 2x. Let me just, something like that, okay? And if we simplify that, we're going to get, oh, what is going on? Okay, 0 to 1, we get 4 plus 2x plus y dx dy. And if I just move this a little bit more here, it'll allow me to actually complete the problem. I'll get rid of that for now because we're done. Let's just do it with respect to x first, doesn't really matter. I'm gonna expend the same amount of work anyways. 0 to 1, 4x plus x squared plus xy, evaluated at 1 to 0. dy, just plug in 1 to x and we should be golden here. 0 to 1, 4 plus 1 plus y dy, so that's just 5 plus y. I can just rewrite that, I suppose, to make it a little bit easier. And we have, of course, 5y plus y squared over 2, evaluated at 1 to 0. Oh, okay. I guess I can, whoa, what happened? I don't know what happened. Okay. We're good now. Move that there. All right. That is 5 plus 1/2, and that should just be equals 11 over 2. And I almost forgot that we need to multiply by root 6. I kept it out because it was a constant, actually. Because it doesn't really matter. We could just really just put it root 6 over every integral, but I just didn't really feel like writing root 6. So we just need to multiply that by root 6. And I guess I will write it here just to make it a little bit easier to see. And that is our answer here. Hopefully that is, okay, it is Z.